Well, good afternoon, everyone. Welcome to EECS151 251A, Introduction to Digital Design and the Integrated Circuit. We are roughly actually 1/3 of the semester at this point. So we're having our 10th lecture, the 5th week. We're going to dig deeper into the RISC-V design, and in particular, we'll talk about how we make our design faster by supporting pipelining so that we can actually run and process multiple instructions in parallel. It's a very important idea in computer architecture design, and almost all today's modern processors are actually using pipeline design. It also makes, remember our view of treating processor pipeline as a finite state machine. So it will also make our finite state machine even more both complex, but also more interesting. There are a lot more states that we need to keep track of, and a lot more control information we also need to keep track of so we can control the states correctly. Before we get there, something interesting also happening these days. This is actually not a new announcement. I think when Intel announced their IDM 2.0 approach, their CEO, Pat Gelsinger, actually already announced it last year, but the news come up again this week, which actually also very interesting from a more system and integration point of view, is that we talk about a lot of interesting development from Intel recently, right? Opening up their fabs to support RISC-V processors also being fabricated, advanced processor also being fabricated in Intel's design. And then this recent news about actually Intel also opening up the opportunities of actually licensing their x86 core. So we discussed that Intel is a very interesting company, has this kind of vertically integrated pipeline, right? They have their ISA, they have their architecture, different architecture, they also have their fab, right? So when they are announcing, they are opening up their fab. Together with that announcement, they're also mentioning that there is an opportunity for folks to actually license their x86 core. This never happened before. So Intel basically built their core and they only supply and fabricate their own core to their customer. They never licensed their core, either soft or hard core, to external partners. This is very different from ARM's model. So entire ARM's business is built on a licensing model, right? Where they design their core, but they license their IPs to a lot of other companies. Like Qualcomm licensed ARM's IPs, Apple licensed ARM's IPs, like Huawei also used to license ARM's IP. So they can actually build their processor, their SoC, all using ARM's design, ARM's ISA. Intel has been actually kept their ISA to their own and also their core. They never licensed that. But this is very interesting. By opening up their fab, there's also an opportunity. Actually, external partners can use Intel's x86 core. So we'll see another x86 core. It may still be fabricated by Intel, but may actually not directly coming from Intel. So it's going to be very interesting. Not a lot of details actually released yet how Intel is planning to do that, but they're likely Intel will have some constraint there. If you're licensing our cores, you need to use our fab so that we can actually fabricate the cores for you. So there might be some string attached, we don't know yet, but this is very interesting that Intel is also opening up their design so that other folks can actually license it. And they also mention this possibility of doing very heterogeneous integration. So you have Intel's x86 core IP, ARM's IP, which you can also license from ARM, and that RISC-V core, you can basically design yourself, right? The ISA is completely open. So there will be a lot of opportunities doing this kind of heterogeneous IPs, heterogeneous integrations on any system. So it's really interesting the way Intel is opening up and actually making their cores even available to third-party designers, and will also make the field very interesting. So again, not a lot of detail. They mentioned they may they may release either soft cores or hardcore core or soft IPs or hard IPs. Anyone know what's the difference between hard IPs and soft IPs? Here we're talking about licensing cores. I will.
Soft IPs probably has to do with like the ISA.
Okay.
Versus like the hard IP could be like the 5 nanometer like technology process.
It's there, but so IP is different from technology node. So node, like when we talk about TSMC, Intel, they are different nodes. But here they are actually both describing IPs, but different types of IPs. Miguel?
Well, I remember reading a little bit of this article, and I believe it's that in the article they mentioned that like the soft cores were on FPGAs and the hard cores were like the physical.
So yeah, so that also, I remember that's also being brought up in the article. So specifically with generally people talking about soft core versus hard core. So hard IP basically means a black box of Verilog code. They dump you a bunch of Verilog code, but not readable. You don't really, it's just impossible to actually decode what's really going on there, very low level. You don't really know. It's still RTL, right? But just very hard to actually figure out. So this basic black box IP, they give you what it is, you can now change it. You just take it, it's guaranteed, has been verified, it's usable, just take it, you can fabricate it with it, right? Get your design, but that's basically a hard IP, just it's hard, you cannot touch it, right? So soft IP, when people are talking about this licensing field, it's more like readable, you can think about like readable Verilog or configurable Verilog. There are like some parameters you can set, like different cache size, different like instruction issue width. It's actually, you can even modify it, right? I actually want a bigger cache, right? Instead of a smaller one. So there are more configuration, there are more control to it, right? So with soft core, you can actually make modification tailored to your use. Like when Apple use ARM's core, right? And now they're designing their own, but they can actually make some changes to it, right? So those are like soft, like the IP is soft, means that we can actually make changes to it. So that's when people generally talking about soft versus hard IP, that's a difference. And then from a licensing fee point of view, it's a lot cheaper to get a hard IP because like, oh, you just basically get dump like just getting a bunch of binary that you can run, but there's nothing you can do, but it's a bit more expensive to actually do soft IP. So that's a difference. So it's unclear whether Intel will do actually hard IP or soft IP or both, but definitely interesting that other SoC providers, system providers will actually have access to Intel's IP when they do their design. So things are getting a lot more interesting. So with all the different IPs, let's still focus on our favorite friend, RISC-V, and see how we can actually make RISC-V run faster. So in the past two lectures, we basically covered different instructions involved in RISC-V, right? All the different type of instructions, encoding, and a baseline data path that can support those functionalities, right? So those are basically the initial implementation. This is the data path we end up with, right? All the different modules and our program counter register file and memory, state logic, all the different components to actually perform the combinational logic, and then the control logic here to actually set different configurations.
I'm sorry, like I forget what the load select does, what that box is for. I didn't see it before.
Right, that's a good question. We also discussed briefly last lecture, right? So load select is right out of the memory port, right? The data port. That's basically right after load when we load the data. And how many different types of load instructions we have, Cedric? 3, right? Right, so we have 3 types of instructions that specify different number of bits we're loading. Loading byte, load half word, and load word. So this load select is basically select which subset of those words that we're actually loading based on the instructions type.
Okay, so kind of like a mask, like you load in the whole word and then you won't choose whatever.
Yeah, I only choose the last byte, or basically whichever byte I'm loading or whichever half word we're loading.
Okay.
Yes, so that's a load select towards the end. So that's a data path that we have. And in today's lecture, we're going to basically start from this data path and optimize it so that we can actually get a pipeline execution with our RISC-V design. So pipelining is a very interesting, simple, but also powerful idea, right, in hardware design, right? So when we actually think about how instruction is executed, right? We mentioned like there are different stages there going through different logic. You will actually do a single cycle data pass where we just let at the rising edge of the cycle, what we have discussed before, tick the clock, and then let the information flow through the entire pipeline, wait until the end of this instruction is executed, and then start our next clock tick, right? Going through a different stage of pipeline will take different latency, right? Because different combinational logic, different modules will take different latency, right? If we think about the time it takes to actually process the instruction, right? Basically all the combinational latency added together with the exercise last time and some like setup time related to register, right? So that will be our end-to-end cycle time. And then we can actually also calculate our clock rate, right? Our frequency here, basically 1 over our cycle period, right? So that's one way of executing. But another way of executing is like, okay, now I actually need to wait. My entire pipeline is actually fully emptied, right? Because I'm actually processing my instruction, goes through the pipeline. But actually my instruction execution have different stages, right? If I'm actually doing memory write back or memory accesses, my register file, my decoding logic, even my ALUs, those are actually idling, right? Not doing anything, right? So why we are actually wasting a lot of time just to like making sure that we're going through all the stages instead of actually doing some pipeline or concurrent execution so that maybe some of the earlier instructions get to the memory write back, memory access or write back stage, while I can actually start fetching the next instruction to get some concurrency going on in my pipeline, in my execution. So that's the fundamental idea of pipelining here. So instead of, so it still takes a while to actually execute my instruction, but I could actually separate it into multiple stages while my cycle time is really just for each of the execution stage, right? Different cycles, actually different parts of my pipelines are active processing different instructions. So with that, my instruction time may actually be longer because I'm actually adding a lot of those registers there, and my cycle time need to be the maximum, the slowest one, right? So that we can actually accommodate everything. But then I can actually get a faster clock, right? So now my clock period is actually shorter. Instead of the entire instruction, it just need to finish one stage, right? So I get a higher frequency. With that higher frequency, every cycle I still produce when I still finish executing one instruction, right? So I can actually also get more instruction out because I'm actually processing at a higher rate. So here it's really a fundamental idea is leveraging concurrency so that all those different parts of the data path can actually be active at a given time, even processing different instructions. So that's a fundamental idea to actually go through pipelining. And the idea is that maybe it takes longer to process the entire single instruction, but we do actually get more concurrency going on so that every cycle, every clock period, we're actually getting an instruction out. So that's the idea of pipelining. And the way look at the way we actually pipeline RISC-V design, we always use, for our discussion, I always use this kind of 5-stage pipeline design, but you can also have different stage of pipeline, right? In your design, you will actually do a 3-stage pipeline. So for illustration, we'll do with this 5-stage pipeline. And whenever we do actually discussion like this, we always have basically a horizontal view and also a vertical view. Horizontal view here is basically resource used for each instruction over time. This is our time, right? So I'm like progressing over time, and horizontally, I see what kind of different components are used over time. And for each given cycle, you look at vertically, I see what actually resources are involved at each given cycle. So there are like 2 views of this. One is over time, the instructions and components are used for each instruction. One is for a particular slot, what kind of components are actually used in executing. So we actually go back to our RISC-V data path, right? We talk about 5-stage execution, right? For every instruction, we first fetch the instruction, right? Figure out the PC, fetch the instruction from instruction memory, instruction decode, right? All the different instruction format we talked about in the last 2 lectures, right? Decode that instruction, what they are trying to do, and also read the corresponding register. You actually doing register read accesses. Then we get to the execution stage, right? We actually need to calculate the arithmetic or logical operations, and also doing branch comparisons. And then if it's actually a memory instruction, we actually do memory access. We actually have memory access stage. And finally, for the final result, we have a write back so that we can write our data back to register, right? So those are our 5-stage pipeline. Again, this is just our design. Pipelining can be applied in any design, right? So we use our 5-stage pipeline. In your project, you may actually do a 3-stage pipeline, and some other more modern processors actually doing 10 plus or 12 plus pipelining, right? So like a different pipeline design. We'll just use this as an illustration focus. So what do we do with pipelining? So whenever we want to actually do pipelining, what we do is that we are actually creating more states, because now actually we have more clock boundaries. Instead of just one clock tick going through the entire pipeline, we're adding a range of registers there so that we can store states for each pipeline the states, so that we are not overriding the different parts data for different instructions. So when we do pipelining, it also means we're adding a lot of registers between pipeline stage. So we talk about 5-state, we're doing 5-state pipelining. There are like different pipelining idea. Is that always better to actually add more pipeline stages? So should we actually, so now we're doing 5, right? Should we do actually 12, 15, 20 stage pipeline, 30, 42, Raj?
There might be 2 things. One of the things might be that if one of them takes significantly longer than the other, then you pull things slows down. The other thing is that sometimes they need data from things that are further on in the pipeline, from before in the pipeline. So if they started doing something else, then you get an error, you get a hazard. So,
exactly, that's a good point. So basically, first, as Raj mentioned, like pipelining, we really want to balance, right? Even with 5-stage, we already see it's really hard to balance, right? Eventually, one of the stage will just take too long. It's actually really hard to do that. And second, there could be some dependencies going on, and just you need the information. You couldn't actually sustain that kind of pipeline. So both are very valid. Any other concerns with very deeper pipeline? Roger.
Yes, like
Jordan.
Yeah, in the limit, like setup time and clock to queue would be longer than the propagation delay.
Exactly. Yeah, that's a good point. So we're adding all those registers, right? We're actually splitting our combinational logic, and then the register access we talk about, we need signal to be ready, like the setup time, so that we can actually capture the logic. And then it also takes time to actually propagate signal right after the clock. All those delay also become very dominant, right? So if you go very deeper, a lot of not only just latency, energy is actually also consumed by register. So it's less popular now, but let's say 20, 30 years ago, a very active research area in computer architecture is actually figuring out the optimal pipelining stage. So what is the optimal stage, right? Because with the benefit of pipelining we discussed earlier, just like, oh, let's go super deep, right? Let's build very deep pipeline. That's also roughly when power became a big problem. You remember, right? In the early 2000, early 2000, right? So the power also become an issue. That's partially with a lot of designs actually builds like super deep pipeline. Then we have a lot of registers going on, and that also consume a lot of power. So building deeper pipeline, of course, it can potentially improve the performance, but also remember all the registers that we are adding in balancing between the pipeline. And we'll also talk about all the different hazards, right, that exist in pipeline that also has overhead. So there's a very interesting and also subtle balance when we actually go to pipeline design. So this is one example that we can actually split the different processing unit into actually different pipeline stages. One thing I want to highlight as we go through this is architecture or pipeline data path in general is a design full of creativity. There are different ways of designing it. I'm presenting a design, This is not the only correct design. It's never the case. I'm presenting one way of doing things. You folks may have different ways of doing things. Whenever you analyze a particular performance, always look at the data paths that you have, how it behaves, and see what's the implications. There is no universal data path that's actually should be the. There's universal ISA. We talked about the ISA already. That's fixed. That's a RISC-V baseline ISA. That's fixed. But there are different ways of designing data paths. So, as an example, in this design, we look at this design. We actually have an interesting another small adder here to do PC+4, where we have actually already, so this value is already PC+4. We already calculated PC+4 earlier, but in this, again, in this particular design, we actually do another PC+4 calculation. This is because, as I mentioned here, we don't want to basically sending, we already need to send PC actually through the pipeline, right? Because we need to calculate the branches, right? Instead of sending both PC and PC+4, we can actually just keep sending PC and then do PC+4 later if we do need the result, instead of adding 2 registers. So with sending every signal down through the pipeline, they say adding more registers, right? So instead of having 2 registers storing both PC and PC+4, we just having 1 register and add a small adder here to do PC+4 calculation, which is still pretty cheap, right? So some design choice is it's a personal design choice. So I put it here. If you like just propagating PC and the PC+4 through the pipeline, that's also a valid design choice. It's just different trade-off. So this is an example of some different nuances actually involved in choosing pipeline. So this is our instruction pipeline here, right? So with the pipeline execution, when we actually have our instructions, now it's getting really interesting. Remember the pipeline execution at a given cycle, multiple instructions are active. They are just executing different parts of the pipeline, right? So now when we actually look at our pipeline, different instructions, the first load is still in the fetching stage, while the decoding stage is actually decoding the store operation. And then we have execute is doing the set less than operation. And then memory access is checking the OR operation, and write back is doing the addition, right? So we have actually 5 instructions involved in the execution, while different stage actually handling different instructions. So this actually makes control signal even more complex, right? So we talk about control, we actually need to specify different control signals based on the instruction that we're dealing with, right? Now the instructions we're dealing with are actually different at different pipeline stages. So one thing you'll realize, especially when you start your project, is that when you do pipelining, we will propagate data through your pipeline. Also pay special attention to your control signal. Make sure your control signal is propagating the same as your data signal. So you're having the right set of control signals controlling your data for that stage. Pay special attention to that. If anything, that's one of the areas you will spend a lot of time debugging with control. Is just the control signals is also propagated through the pipeline. The different stages having different instructions, and each instruction has its own set of control signals. So now control become a lot more complex because it actually needs to handle different instructions. And we'll see more control signals getting even more complex because there are some special cases that we have actually in our data paths to improve the performance that also makes the control even more interesting, let's put it this way. So with that, we talk about our basic 5-stage pipeline, right? So Viraj actually already hinted earlier, right? When we have very deep pipeline, there will be some dependencies that we cannot satisfy that we have to actually start our pipeline that actually cause performance issues, right? So that's what we call hazards. Generally, there are 3 types of hazards: structural, data, and control. We'll go through them, and also some of the ways that we can actually overcome those hazards in our hardware design. So pipelining hazard. So hazard is basically a situation that we cannot actually process every instruction every cycle. So ideally with pipelining, right, we mentioned we want to have every part of our pipeline actually active all the time. So with that, we want to basically start a new instruction every time, right? But there could be some fundamental challenges or issues that stop us from doing that. What are some fundamental issues? For example, the first one is structural hazard. As the name suggests, right? So it's basically, I need a particular resource to actually execute my instruction. But by the time actually I'm starting, I don't have that resource. So I need something, but current pipeline, everything is busy. This resource is actually used by some other instructions. So I cannot actually start my execution. So this is a more resource, more fundamentally bonded to hardware, not enough hardware. Later we'll see not enough resource is actually the simplest problem. If we don't have enough resource, let's provide enough resource. So this is actually the simplest hazard that we can basically handle by adding more resources. That's a structural hazard. The second one related to more intrinsically to dependencies or to data or instructions. It's really between those instructions. It's not like I don't have the resource in hardware. Like I don't have the data. I'm waiting for something else, but something else haven't actually finished yet. I'm looking at this register, but this register haven't been populated, haven't been initialized. With that, I cannot start. So this is actually a lot harder to solve, right? This is not something that we can just put more resources there. Even we have more resources there, this won't be solved because this is actually very fundamental. We have to actually wait the previous instruction to actually finish. We'll talk a little bit more for this. There are some opportunities in the sense that maybe it's not really available. We look at this particular point, but there are some other points that the data may be already computed. It just not arrived to this destination yet. And we can do something very interesting and very smart by actually grabbing that data in later part of the pipeline, though it hasn't actually arrived to the specific destination. We'll talk about that. This in some scenarios can also be handled. Control hazard is also very fundamental to the program, right? We spend a lot of time talking about the control, but then you have a branch, it actually goes to a different place. There's nothing we can do, right? Because we actually jump to a different place. We haven't actually get our branch resolved until later part of the pipeline. So we still need to stall to figure out where we need to go, right? Figure out where the program counter needs to be. If anything, we'll talk more later. Interestingly, architecture and the machine learning are actually two distinct fields. Typically don't overlap. I think with more recent overlap is really like architecture, the hardware enabling a lot of machine learning processing, right? Control hazard is one of the areas, very interestingly, in architecture that actually has very early adoption of machine learning ideas. So a lot of idea put into to resolve, to at least alleviate the problem with control hazard is actually doing branch prediction. And whenever there's involved prediction, right, some kind of learning algorithm could actually potentially help, right, in a lot of our modern processors. We actually have some neural network doing branch prediction. So we'll also talk about that. It cannot be handled easily and also deterministically by hardware. Some more learning-based techniques can make this prediction easier. So with that, let's start exploring the different type of hazard. Before we move on, any questions, comments, thoughts, things come to mind when we talk about hazards, pipelining? Cedric?
So you said to solve control hazards, some chips have a dedicated neural network part. So that's what's being advertised on a lot of chips then.
Yeah, and this is actually not something new. This is actually 10, 20 years ago, even before AlexNet deep learning stuff actually become the dominant. It's actually a very simple, basically a very simple MLP. It's actually doing some doing branch prediction there. And that's actually even before the entire whole deep learning takeoff. It's just works pretty well actually doing the branch prediction. And that's actually being incorporated into the branch predictor design. Another thing with hardware is that, of course, so then we get to the trade-off part. We could actually build a very complex model to do the branch prediction really well. but then that also makes the hardware more expensive, right? So there's also a trade-off. We need a good enough branch predictor, but also not too expensive to actually make it infeasible to do the design. But yeah, a lot of today's hardware, especially AMD's process, early adoption of branch prediction idea using neural network, machine learning is actually in AMD's process. Question?
Is branch prediction kind of different from prefetching?
Yeah, that's a good question, Brendan, right? Yes, so they are related, both prefetching, whenever you have something, right? You want to predict something that hasn't happened yet. They are different in the sense that prefetching is more fetching data. So prefetching is talking about, I don't know whether I want to access this piece of data or not, but I have a strong hunch that this data will be used later. Let me prefetch that data from, let's say, DRAM to my cache. This can be done either by software, there's actually prefetch instruction you can use, or by hardware. Hardware also has some dedicated prefetcher unit to fetch data in there. While branch predictor is also related, it's also doing some prediction. I don't know where I'm going, but I think very likely I'm going to this place, so let me predict. And then this is a hardware engine to actually predict instruction, right? Predict which instruction, which address I'm going to fetch. So they're related in the underlying idea. I'm doing some prediction, but the target is different, whether targeting data and address. So for prefetching, there are also, I think one of the recent work from Google, they are actually also doing machine learning enabled prefetching. A similar idea with a lot of data, we can predict which data is actually more likely to show up. Today's hardware prefetcher is still pretty simple. It's more like, basically most of them just support like streaming prefetching, right? So I'm accessing array, right? I'm actually just scan this from beginning to end. So very likely I will actually fetch something later or with some strided execution. So today's hardware data prefetcher is more doing this kind of very simple prefetching. But both are related, involve some prediction, but one is for data, one is for instruction. Good question. Anything else? Anything else you're wondering? Okay, great. So we talk a lot about a hazard and the potentially ways to solve this, right? Let's go through each of them and to see what are the problems and how we can address them. So structure hazard, we talk about it. This is more related to resources, right? A particular structure is actually being used by multiple instructions, right? So what can we do with it? Well, of course, a simple solution was see this simple solution a lot of times. Like whenever there is a computation or whenever we're contending some shared resources, right? Let's just take turn, right? Let's make sure one instruction have it first, and then the other instruction stop until it's their turn, right? So stop will show up a lot because we cannot handle all of them in parallel, so we have to actually take turn. Another solution, alternatively, instead of fighting with limited resource, right? Why don't we just make the pie bigger? Let's just add more resource there so that now both instructions or different kinds of instructions can actually do things in parallel. So whenever we talk about structural hazard, if we do have more area and power budget, that can always be resolved by adding more resources. So this is one of the easy ones because we can always resolve it by adding more resources. But sometimes you may not have that much resource, right? So this, again, hardware design is a lot about trade-offs, right? But this can typically be resolved by basically building, adding more hardware. For example, one thing, a good example of a hazard is register file, right? We talk about, we have this register file and we need to actually perform read and write operation, right? For RISC-V instructions, especially R-type instruction, we need to read 2 operands from the register file in decode stage, and we also need to write 1 value in the write back stage. So there can potentially 2 places have hazard or have contention here, right? So the first one is that we actually need to read 2 in parallel, right? Because we have source 1, the source 2 register, right? So now we actually, we will have register file, we can only read 1 data out per cycle. We cannot actually get both source operands, right? So that's the first structure hazard. That can easily be resolved by basically adding another read port, right? So now you have 2 read ports, we can actually do 2 parallel read per cycle so that we can actually read both operands in one cycle. So that's a very simple example. It's a very easy way to actually support parallel access and also resolve structural hazard by basically adding more resources. Another one is actually doing write, right? So here we also have, even in our discussion, because register read and write are so critical, right? So we basically always have to have a dedicated write port with register with 2 read ports and 1 dedicated write port. With that, we can actually have 3 accesses per cycle. We can support 2 parallel read and 1 write. Later in this semester, we'll talk about how we actually build register file. Typically, register file are actually more built as a SRAM, as an array of memory. When we actually see SRAM, we'll talk about how we support, how we design actually multi-ported SRAM in CMOS logic, in transistors to actually support this kind of parallel accesses. You will actually add even more parallel ports, like for example, we're building a vector processors, we actually have more concurrent executions. Sometimes we actually want to even have more parallel accesses to our register file. So memory read and write, register read and write is always important. And typically, especially for this kind of behavior, we always support parallel multiple register files to actually meet the bandwidth demand. So that's for register file. So you will look at our pipeline here, right? So another potential hazard, we talk about register, another potential hazard is actually memory, right? So any kind of state element that actually potentially can be accessed concurrently can cause a structural hazard. So one potential place is if we actually look at our pipeline execution, is actually between the 2 memories we have, data memory and instruction memory. So far, we have been basically having this assumption. We are basically trying to work around structural hazard by having 2 separate memories, right? One for instruction and one for data. In a lot of older designs, we're very limited, or it's actually a different flavor of designs by basically consolidating instruction and memory into a 1 unified memory structure, right? So that we can share, right? Maybe I don't have a lot of instructions, so I can actually use my instruction memory for data, or I have very complex instruction pipelines, but they're operating on very simple data. I can actually dedicate more memory to my instruction, right? So that also allows this kind of trade-off. So that's also another flavor of design. But then that can also trigger a structural hazard on memory. So in our discussion, we basically typically use 2 separate memory so that we don't need to worry about memory hazard. But again, this kind of hazard can be always resolved by having more resources. So just a quick recap. This is just a very common hazard, show up a lot in pipeline processors, but also one of the easiest one because it can always resolve by adding more resources. In our particular RISC-V design, if we are actually using a single memories, we need to do both data accesses and also instruction accesses. Again, if we have limited resources, we cannot put more resources there, we need to stop. So that's if we have a contention, we cannot resolve it, we just have to wait. So that's one way to do it. And typically, in most of today's designs, we actually have separate instruction data, especially for this class, we'll mostly have separate data and instruction memory so that we are not limited by either instruction access or data access. And in generally, when we actually design ISAs, one thing we notice is that we only have at most, right, 2 reads and 1 write. We never have like a lot of reads from register file. We never have more than 1 write to register file. So overall, the ISAs also limit the concurrency that need to be supported in our data path. So that's the first hazard that we see a lot when we actually handle pipelining, structural hazard. Any questions, comments, thoughts? Brendan?
So is this the only structural hazards that can happen in a RISC-V 5-stage pipeline, or are there like more that we're just not discussing?
Well, again, so it's there could again, this is related to data paths, right? So if we look at this data path, so for this data path, well, we actually also already resolved a lot. Like, for example, hypothetically, a potential design could be, instead of having a dedicated branch predictor, I'm actually using my ALU to do the branch comparison, because branch comparator is basically doing a subtraction, right? Comparing two results. I could have also using my ALU for that. So with that, there's another hazard, because to resolve the branch, I need to use my ALU to actually compare the two registers, and also use the ALU to actually calculate the target address, right? So that could cause another source of structural hazard. So it's very data path specific, right? So we are using this, like another hypothetical example. I don't even want to have this adder. I want to use my ALU to increment my PC, right? So that will create another structural hazard. So here we are mostly talking about in the context of this data path. But again, I mentioned earlier, right? Different data paths behave differently. So we can have different theories with this data path, and then there will be more structural hazards. Yeah, so whenever we talk about hazard, always very specific to a data path. Yeah, good questions. Any other thoughts, questions? Okay, so this is this data path, and we talk about structural hazard, and let's move on, see what question.
For example, is the value that calculate the previous for the next instruction, we use the output from that. Will that also calculate?
Oh, that's so you're wondering what if an instruction is actually using the results from the previous instruction, right? How would that's a good question. That's exactly where we're going. We're going to talk about data hazard. And I don't think I've talked to you before. What's your name?
Anna.
Anna, right? Good question. So Anna asked this question that actually leads naturally to our next topic, right? So we only talk about structural hazards, and we have this very positive view, right? Let's just make the pie bigger. But sometimes it's actually very hard to make the pie bigger. Another potential issue, like Anna mentioned, right? What if my data actually, I'm actually using the data calculated from the previous instruction, right? And then if we don't have the data, I cannot move forward. So that's basically what people use, describe for data hazard. So data hazard is actually a true dependency between instructions, in the sense that I'm using the previously calculated data for my current processing. Let's say for this example, we're illustrating here. So we have an addition here, right? So we're adding T1 to T2 to T0. So I'm writing to register T0 in this stage. And later part of the pipeline, I'm actually, well, I have a lot of dependency here. I'm actually, like for this highlighted here, I'm actually using store T0 to my memory, meaning that I actually need the value of T0 here, right? So this is also a dependency in the sense that I need to have this is a value I'm actually writing to my memory, and it won't be calculated until the end of the pipeline where I'm actually writing where this instruction, the first instruction, the add instruction is really populating the value, T0 value to data path, right? To the register file. So this is basically what we mean by data hazard. It's like I'm actually dependent on this data, but I cannot move forward without this value. For the particular case that we highlighted here, this is actually easier to resolve for this particular case, because the hazard happened in this cycle, right? So when I'm actually writing to the register from the addition and then reading from the register. Remember we mentioned like write happens synchronously with clock in our register file, right? We have a clock signal. Whenever clock ticks, we do the write, and read happens, again, in our data path, in our discussion, read happens combinationally, right? So read happens anytime. So in this particular case, we can actually, this is actually not a true hazard, again, to our data path, because I can, in this clock cycle, right, we're talking about this stage. And when clock ticks, so the data will be actually ready in the register file when clock ticks, right? Because I'm doing a write. And then when I read, well, I only need the data to be available before the next clock edge, and read happens combinationally, right? So we can basically assume if write happens, let's say the beginning, right after the clock cycle, let's say the first half of the clock cycle, when I do the write, when I do a read later part of the clock cycle, the data is already available there, right? So this can be resolved because our assumption that write happened at the rising edge of the clock synchronous to the clock, and read happened combinationally. At a very high level, you can assume write happened at the first half of the clock cycle, and read happened at the second half of the clock cycle. So read always get the right data. Brendan.
Are we using T0? Like, are we reading from it to the third instruction?
Yes, so I'm getting there yet. So that's a good point. So T0 is also a true conflict for the third instruction. But for the one that we're highlighting here, that just happened to be resolved because the register write happens at the beginning, while read happens combinationally. We can always grab the up-to-date data for this pair. Make sense? Make sense? Okay, good. So that's again for this discussion, right? So for this discussion, we use this, and if you notice the shading, so typically when you look at any pipeline data path, you'll notice the shading is basically highlighting write happened at the first half of the cycle, and read, assuming read happened at the second half of the cycle. But that's not the truth. That's just make it easier to explain. But fundamentally, it's because write happens synchronously with clock, read happens combinationally, right? It's just always being updated. So Brendan already mentioned, right? So here, it's not only just this store, right? T0 is also used here, right? So this, although it is a data hazard, it just naturally with our register file policy, it can be actually resolved easily. But for other type of hazard that we have here, we actually, to handle that, we actually need to have some other mechanism to resolve them, to guarantee that we can actually have full throughput. So let's take a look at how we do that. So now let's take a look at another example where we, instead of T0 S0, but it's basically used everywhere. So every instruction after the first instruction is actually using the value of S0, which is being initialized in the first instruction, right? So here, this value of S0, 5 is old data, and the 9 is new data. So we talk about, so far, we only talk about the register file, right? So basically, this and this dependency, they are so far away, right? So this can be resolved. But we also have the problem here, right? So with the subtraction, at the beginning of ALU, we actually need this data, right? So this is also arithmetic logical operation at the beginning of ALU, we actually need this data, right? So how do we actually handle this? Do we have to stall? Because now it's a true data dependency, right? There's nothing we can do. This is fine. This is fine, right? Because we can always get the real data. What about the other two, the earlier ones? Brush?
You would need to use forwarding, right?
Yeah, so now it's something very familiar, right? So in your beautiful 61C experience, right? The magic, great ideas in computer architecture. One of the very important and interesting ideas is forwarding. So this is what I discussed earlier, right? So last two instructions are fine, but the next two, the first, second, third, fourth, fifth, right? So those two, the fourth and fifth are fine, but those two are the harder ones because we don't really have the data. So well, before I think variety is very advanced, right? Again, before we talk about forwarding, one thing is that basic things always work in architecture. Without fancy things, we can always stop. That's basically your principle. If there's no resources, I don't want to do any fancy logic, we can just always stop, right? So instead of processing every instructions, because I'm using the previous data, I just add bubbles to my pipeline. I don't do anything, right? For those 2 cycles, until my data is ready, right into my register, and then I can read it in my execution, right? So this is basically no up in in your program. We just don't do anything, so that we let the pipeline process. So eventually until the data become available. So this always works. We can always stall, right? So as we see stall, while it actually works, it hurts our performance, right? Because we are wasting 2 cycles, not doing anything useful, right? We're just doing bubble. We're not doing anything useful. So this will always hurt performance. And this can also, sometimes compiler can also do interesting things. So one thing you will see with architecture compilers, like compilers sometimes can do also instruction reordering. Instead of having such tight dependencies, we could add some other instructions that don't have those dependencies in our instruction sequence. So that also works from a compiler. You will see actually a lot of interesting research from compiler doing that. But now, as Raj mentioned, from more hardware architecture point of view, to resolve that, there could actually, this could also be handled in hardware. Again, by having some additional wires and also control signal. Again, very important. There is also associated with control signals to actually forward the result. Why do we call forwarding, right? Just quick recap, as the name suggests, right? Although we say the data become visible when it actually writes to the register, right? The register file is architecturally visible, but the value is actually already calculated. The value of our register here as 0 is already calculated. We're doing addition here, right? Already calculated after the execution stage. So after the execution stage, this value is already ready, but it just takes 2 more cycles until it actually propagates to register file. The idea is also very simple, right? We don't need it to be architectural visible, right? Why don't we don't need to wait for it, right? Let's just grab this data directly to my input of my execution, to my ALU, so that I actually grab the data directly. So this is, in some sense, breaking the abstraction a little bit. So in the abstraction, we basically, all the instructions communicating through register. It is still the abstraction in your ISA, in your program, but under the hood, when architecture, when hardware is processing it, hardware sees everything, right? Not only just register, hardware also sees all those wires, right? All the wires actually communicating back and forth. Hardware is like, oh, I don't want to actually wait until register because I clearly see this value outside my ALUs. Why not I take the full control and bring that value to the next executing stage and completely hide this from the programmer and also higher level abstraction. So this is a pure microarchitectural changes. It's not really visible. It does not need to be visible to the higher level programmers. So that's basically the idea, forwarding. Forwarding results in the pipeline, in the wires in the pipeline directly to where it's needed, instead of waiting to be shared either through registers or memory. Let's take a look at our example that we seen earlier. Like I think Brendan mentioned, right? So we have a lot of dependencies with T0, right? All the later instructions are using T0, and we talked about the last 2 are fine, but the second and the third ones are the problematic ones because it just we cannot get the new data so early, the updated data so early in our pipeline. So what are we trying to do with forwarding? Is basically to grab the data early whenever it's actually available. So again, this is addition. The data is already available after the ALU, right? It's already pre-computed after the ALU. So for the second instruction, when we actually think about inputs to our ALU, instead of directly getting our value from register file, but those are actually will be stale very soon, we can actually have another input. This input is from the previous calculated results from ALU as our input to our execution stage and pick that as our input. And similarly, for this ALU, it's actually after the memory stage. In the write back stage, we can actually pick a different input to our ALU. So now our input to our ALU doesn't always need to be register, right? Before it's either register or PC, right? So that's our input to ALU. So now it can also come from intermediate state inside my pipeline that is not architecturally visible. So before, all the input to my ALU are actually architecturally visible. Program counter registers are both architecturally visible. But now I can actually grab intermediate state inside my pipeline, but I know for sure, because looking at the instruction patterns, they are actually correct values. And then I can take that directly. So that's basically the idea of forwarding. So in this example, again, there's a control logic, right? We actually need to do like architecture trying to hide all the details, but architecture also need to make the judgment call in the sense that this is a valid case of forwarding, right? So we actually need to compare the two instructions. One is actually in the execution state, the destination of the previous instruction actually do match the source register of the current instruction. If we find a match, we actually do the forwarding, right? So when we actually do forwarding, again, remember we discussed a control signal, right? There's one more control. We'll see the data path in a minute. There's one more layer of control because we need to pick which is the input to our ALU, right? So to set that clearly, we actually need to compare the destination register of the previous instruction and the source register of the current instruction. So that need to be considered. One corner case is we must ignore writes to one particular register, X0 register. Why we need to ignore writes to X0 register? What's special about our X0 register? Cedric? Yeah, it's always 0, right? When we do a no op, we just write to 0. So be very careful, right? If it's actually write to 0, it's actually not changing that. So that's one thing we actually need to, we never update our X0 register there. So there are also corner cases we actually need to consider. So we talk about comparison. We also talk about forwarding logic, right? So once we actually, let's say, space limit, let's mostly just forwarding one of the, let's only for, in this only forward one of the operands, but we can do both, right? So we could also do another forwarding logic here. So as we mentioned before, it's either input to our ALU, either from register file or from PC, right? So those are the two architecturally visible states to our ALU. Now with forwarding, right? We talked about earlier, it can either from previous calculated results, right? So here is a previous calculated results. I basically, from my ALU, I just forwarded back one scenario. Another could be actually the result actually being written back to our register. I can also grab that result so that I can actually use in my input of ALU directly, right? So again, we need control signal to select the right scenario, right? So if there are one instruction apart, I forward from ALU to ALU directly. If there are two instructions apart, we actually need to do right back to ALU forwarding, but this requires control logic. Question?
Yeah, sort of a question about instruction memory. Like I noticed on the diagram, it also has like the shaded group, right? Why is that? Like I thought you can't track your instruction.
Yeah, so this is more just we have a stack of slides and we're using this. Yeah, so this is we are not writing to the instruction memory. My guess that is actually structured this way. Why we actually structure this way? Why do we actually shade the instruction and we don't shade any data memory this way? I'm not sure. My hypothesis, I don't even have a hypothesis, but I'm not sure. I think it's just the slides illustrate this way. But in our discussion, read to our both instruction memory and data memory is also combinational. So whenever the data, so I guess partially this is shaded the same as register is showing the data is available immediately because read happened combinationally. But I'm not sure why it's shaded this way with the first half. Let me get back to you. Let me look at the history of these slides. Any other questions? Anna?
Without any improvement, only ignoring. Because we are living a larger scale, like everything is like the any, we only use it slowly, is that still considered inefficient?
Oh, you mean whether like, oh, let's just stall for one cycle. What's the big deal of that, right? You know, oh, that's really interesting. That's a good question. So if we're talking about, oh, we have the whole pipeline busy for, let's say, 1,000 cycles, and then we just happen to stall one cycle, right? So in that sense, yeah, you're right. It's not a big deal, right? Just like, anyway, we need to actually delay. Well, just something happened, let's just stop, right? But in a lot of this kind of scenarios, right? So those are, instead of corner cases, like one happened like once every like thousands or tens of thousands instructions, those could actually happen very frequently. Like say every couple instructions this happened, right? Like just think about the way we write program, right? We calculate some result, we use that result in the next operation, right? This kind of dependencies actually show up very frequently. So instead of happen like once every thousands of instructions, this is more like happens like at once every 5 instructions, like or 10 instructions. So this could be actually very significant. Just think about the way we write program, and there are always dependencies between instructions. So with that, those stall can actually be very, because we are stalling like 20 or 30% of the cycles, because it just happens so frequently. So this could be actually a big deal in a lot of scenarios. And this, so both this, and we'll talk about branch hazard, that's also closely correlated with the way we write program, especially writing loop with very small loop body, and then we actually do a lot of branching, right? So you will just like do misprediction once, it's not a big deal, but every 3 instructions we do a misprediction, then our pipeline is basically always doing wasteful job. So that can be very significant. Yeah, so it's a lot about the frequency. And when we talk about those patterns, those are actually show up very frequently. Okay, so forwarding logic. Any other questions on forwarding, pipelining, data hazard? Okay, great. With that, any announcement? Let's see. Well, reiterating midterm happening in 2 weeks, I guess in a week, not the next week, but the week after. We'll cover this topic basically by this lecture, by pipelining. So next week will be a relatively slow week. We're not introducing new material, at least new material we have covered in the midterm. So basically to this lecture, you can bring a handwritten note, 1 page, can be double-sided. Don't need to copy anything on the RISC-V green card. It will be provided as part of the exam, so we will just print it ourselves for you, so you don't need even to bring that, and you don't need to copy anything on the RISC-V green card. We will have a review session, and the room we got is the same room, this room. It will be next Tuesday, 5 to 7 p.m. So all the GSIs will be here. We'll go through a couple past questions. We'll also do the discussion, so it will still be discussion next week, that you can also use that as a small review session. Again, no new lab this week. Hopefully you folks are wrapping up lab 3 and lab 4 at this point. And we do have a new homework. Again, this will be the last homework before midterm. It covers up to pipelining. So definitely take a look at it. It will be due next week. So use that homework, also help you to review the material. Any questions? Well,
yeah. For the green card, I noticed when I was doing the homework, like one of the green cards we had provided didn't include like the opcode, like the binary versions, like the opcodes and stuff. But the one from 61C did, and do you know if this RISC green card includes like the binary for like the opcodes and the fun3, fun7 stuff?
We will, if the green card, so is the 61C green card is basically a superset of the green card we have? Are we saying?
I'm not sure.
The old 61C one is.
The old 61C.
The new one is not. The new one is pretty similar. There are multiple of them.
Okay.
Some of them has the binary versions of all opcodes and the fun3 and fun7 for each instruction.
I see.
And some of them just say this is the.
This is what you guys have. It's like the green card, and it's the Open RISC-V, and I couldn't find any like actual binary on here.
I see.
Or even like hex.
Okay.
For like I-type like sub opcode and stuff like
I
that.
see. Understood. So I will guarantee, I need to take a look at the both different versions of the RISC-V green card. I think worst case we can do is just print a bunch of RISC-V green card towards the end, but it will have all the information. But I'll take a look at and pick basically the superset that has all the information. And the bottom line is that you are not supposed to remember the binary coding of all the different fields. Yeah, you don't need to remember that. Don't make notes there. If we want to test you, it will be provided.
So before the exam, is it possible for you to like say this is gonna be the green card that is gonna be on the exam so that we can like come?
Yes, so I'll make sure I'll announce which green card it is next Tuesday, basically. Yeah. Homework draws. You mean slip days for homework? Oh, we don't do homework drop, but you do have, if I remember correctly, 7 slip days for homework and 14 slip days for labs. We don't do homework drops. Any other questions? Okay, good. I wouldn't worry too much of the midterm. If anything, we do midterm just so that you don't have a big final in the end. So here is basically we already covered some of the materials, and we'll also offer clobber opportunity for final if you don't think you did too well in mid. But I wouldn't worry too much about the midterm. Okay, just an opportunity to review what has been covered so far, because we're going to start our CMOS and the digital logic part of the class that will be very different from things that we have seen so far. Okay, so with that, let's get to the final. We already hinted a little bit earlier, right? So we have data. We'll talk about control, right? What if actually branching, we actually jump to different places? How do we actually handle that? So this is a data path that we have seen so far, right? One thing we want to highlight here is related to control, right? We need to actually figure out when the target PC is actually calculated here. So which stage you actually need to, let's say we do a branch instruction, which stage? So we have instruction, instruction fetch, instruction decode, execute, memory, and write back, right? So in this pipeline, when is the target PC program counter is actually calculated? When do we actually know you will have a branch instruction? Where are we jumping? A lot of signals, Raj. After the ALU execute, right? Because we actually need to calculate, we use ALU to calculate the PC, right? We mentioned one of the input is PC, right? So this is a final target PC in the memory stage. And this is one of the paths is going back to our program counter, right? Again, every data path is different. So that's why, and one thing I mentioned here, this is in this data path. This is where our PC is calculated. Different data paths draw this differently. In this data path, it's pretty late, right? It's not resolved until memory. I don't know where I'm going until my current branch instruction gets to the memory stage. This can be problematic because if I actually have a branch, right? If I want to get to the next, so again, it's resolved here, right? In the memory stage. In the next instruction, I need my PC when I fetch instruction, right? I don't know where I'm going, right? We talk about control, like prediction, right? Let's assume we just continue our execution, even though we don't know where we're going. The next instruction, you need to actually fetch PC here. Again, I still don't know my PC yet because I only get this resolved in my memory stage. And then finally, actually, when we, in this, we also regard this. This is solved. Right, so in this case, I have my data register here, but this is actually, I actually got myself confused. So if we go back here, so this is actually being propagated here, and it will be updated in the next clock tick, right? So I become available in the memory, but it's actually being loaded to the PC actually in the next clock tick. So in this setup, so even in this clock cycle, it hasn't been actually, so I'm still loading the previous PC, right? So this is still not updated. And until the third instruction, the fourth instruction, and that's where actually I finally figure out I'm supposed to jump instead just execute continuously. And all the instructions that I have actually executed are actually not useful because they are not supposed to show up in my pipeline. Right, so this is basically the challenge with branch operations because we don't know where we are going. We have to make some guess, and we may actually guess wrong, right? So basically, if the branch is not taken, then we're doing the right thing, right? We basically fetch instruction continuously, and those are the correct instructions. But if the branch is actually taken, right? So we actually need to flush all those incorrect executions because they are actually not useful, right? So back to our instruction sequence. In this case, if we actually, finally, when we realize it, we actually execute the wrong way because we're actually supposed to jump. All those instructions actually need to be flushed because they are not part of the execution. Brendan.
Is it possible for like one of those incorrect instructions to like write to the register file or to memory before you flush them?
Yeah, so that's a good question, right? So you will look at our execution, right? So all those three instructions will actually be flushed out, right? Well, any of them actually could potentially, so it's basically flushed out here because this is when our data is actually realized, when it's actually resolved. If we look at the next, so basically it's changed the, it will only change the architectural visible states, right? That's what we are actually worried about. And architectural visible states are basically either registers or memory, right? Let's see whether it's actually touching register or memory. So in this case, we are not writing registers, right? So we haven't actually updated the states yet. In those cases, we are actually either doing execute or either doing decoding. We are also not actually changing the state yet. So in this case, we are actually not updating the state. Again, in this particular data, every data path is different. In this particular data path, we're not changing the state. If this actually in a different data path, it has a concern, we may actually need to just stall the next instruction, always stall at least the immediate next instruction to avoid this scenario. But in this data path, that's not the concern. Good question. So reducing the branch penalty. So we already hinted, so we have the flushing overhead. We already hinted that we could actually do branch prediction to guess which way branch is going. And so Anna mentioned the cost, right? I had this example, you were doing a loop, right? So we actually do a lot of branch. It's actually very easy to predict, right? So the loop is 1,000 iterations. It's only, the majority is basically go back to where we start, and only one is actually loop exit, right? So with that, so we can actually do branch prediction. So if we have seen a branch, we actually say, oh, it's very likely this branch is taken. So we actually go directly to the label to actually execute this branch. And then when we actually get to this stage, we realize, oh, we make the right prediction, our guess is correct. And that's, so we don't need to do anything. And then we only need to actually flush our pipeline. You will actually make a wrong prediction here. So that's basically branch hazard, control hazard is again, now we're talking about how we're actually making sure we're executing the right instruction based on our data path. Any questions, comments? A lot of hazards in this discussion. Raj.
So if we get it incorrectly, how do we go back?
Oh, you will get, so in this case, you will actually guess we are taken, but
Yeah.
what if actually we don't taken?
Yes.
I see. So when the branch is resolved, right? So we actually can figure out the right PC, right? So instead of using the predicted PC that we have been using. We basically really just following the pipeline. So this instruction will naturally update the PC, get to the right PC. If it actually matches the PC I'm using, I don't do anything, but if it doesn't match, actually just revert back to this PC and do my calculation. Mhm.
Wait, so if you predict that you're gonna jump, don't you only get that out like on after ALU, but that's like why that for next one.
So if I predict I'm going to jump, I don't have the label until,
Like even if you like forward it after the ALU, but it is not nil.
oh, I see what you're, so again, in this particular design, the reason I need to actually wait until ALU after the execution stage is actually doing the branch comparison in the execution stage. I could have, again, so when I do branch prediction, I also need a new logic there to actually do the address target calculation. I need to put new logic there. So basically, if I have a prediction strategy to predict either taken or not taken, I can always calculate the target, right? As long if I have the current PC, I have my my label, my offset, I can always calculate the target early, have a dedicated ALU there or dedicated adder subtractor there, right? So I don't need to wait here. There are two things. One is calculating address, but calculating the address can actually be done earlier. That's a very interesting question for, and let me spend a little bit more time here. So the reason we are doing branch here, the ALU calculation for branch, all the information can actually be get from the instruction itself, PC, current PC plus the immediate offset, right? The reason it is actually after the register file is because we're doing the register comparison here. That's why I actually need a dedicated, I need to read from the register, right? If I don't care about the comparison result, once I actually have my instruction, I can have a dedicated like a branch predictor. And in my branch predictor, I can have basically an adder here to calculate the target instruction directly without accessing my register file. Make sense?
It's a dedicated hardware that is your instruction is.
Either taken, or I guess a branch predictor.
Instruction, and you just know the offset.
Exactly. So it's instead of I guess PC plus 4, your PC plus the offset, PC plus the immediate from the instruction. You could get it there.
So you will read the label at the last part of the instruction and say, oh, you want to go there. So you don't, it doesn't need to even dip into the register, into the registers and see, it just takes the last part of the instruction and says, this is where you want to go.
Right. So let me do this clearly. So when we do this, so there are two parts. One is branch prediction, and one is the target address calculation. So for target, let's put how we do branch prediction aside. So you can always predict, always taken, always not taken. There are like different branch prediction strategies. But to calculate the target address, I only need the current PC plus immediate. All both I can get basically after the instruction is resolved there, right? So I don't need the register. So that's what we discussed so far. How branch prediction happens, there are like a lot of different ideas, always taken, always not taken. A lot of branch predictor is actually using the instruction address as an input to actually train different patterns. So it's actually for different instructions, different branch, I may have different strategies here. So this can be an interesting unit on its own that takes some, you think about any machine learning pipeline, takes some features that as input, but the output is a binary choice, whether it's taken or not taken. While that if it's actually taken, the target address can be actually calculated directly. Okay, so that's control hazard. We're already at 2, very interesting discussion, and we'll spend more time in homework, in discussions, in review, cover this topic, and this will be basically what will be covered in our midterm. So with that, good to see everyone. I'll see you next week.
Thank you.
No problem.